We need to talk about this data pre-processing. So we will cover some parts which has been done last time. So in separable data sets, it's linearly, data sets could be linearly separable, which is a property of two sets of points. So these two sets are linearly separable if there exists at least one line in the plane with all points of the first set on one side and all points of the other set on the other side. So it's linearly inseparable if we can. It's linearly inseparable if we can use a single line and try to divide the data sets into two different groups. So one set will be located on one side and the other set will be located on the other side. So in this case, we can say that it's linearly inseparable. When it is in two-dimensional space, x1 and x2. So this data set, we have two features, x1 and x2, and we will find, maybe we can generate this line by a perceptron, for example. It could also be generalized to higher dimensional Euclidean spaces if the line is replaced with a hyperplane. So it could be in three-dimensional space. So we have x1, we have, for example, x2, and we have also x3. So in this case, we need to have a plane, a hyperplane to separate those two different sets of or two clusters. Inseparable, it's otherwise. All inseparable data sets, it's in otherwise. For example, in this example here, we have two data sets. It's a green and red, for example, and it's difficult, in fact, to find a line which can separate them into two different groups. In this case, we need not a straight line, but something more complex. So maybe you can get something like this one, right? So it could be something like this one. So in this case, the red will be located above the line, and the green will be located below it. So this one, it's non-linearly separable data set. We have very famous example, which is the XOR, which is binary classification problem. And in the XOR, we have two inputs, 0, 1, 0, 1, 0, 0, 1, 1, and the output will be 0, 1, 1, 0. And when we plot this data set, we can see that we have the 0 and 1, green and the blue, for example. So this is one group, and this is the second group, for example. And it's difficult to find a straight line which can separate it into two different groups. So for example, if I selected a line like this one, in this case, the accuracy maybe 0 is correctly classified, but 0 here is misclassified. This one is correctly classified, this one is incorrectly classified. So in this case, what will be the accuracy? This one is correctly classified, this one is correctly classified, so it will be 2 divided by 4. So the accuracy will be 50%, right? If you selected this line. So if you selected another line, which might be like this one, it's the same also, we will get an accuracy which is 50%. So it's difficult to find one line which can differentiate or which we can divide those two classes into two different classes, one in one side and one on the other side. So in this case, we can say that this XOR data set, it's linearly inseparable, right? It's difficult. And as you can see here, when we need to classify it, we need two lines. So I need to put a line here, for example, and I need to put a line here. And in this case, we can say that all data points between the lines will be classified as 1, and the other points will be classified above and below. It will be classified as 0. So in this case, minimum, we need to have two lines here, as you can see here. So it's two lines. And we have here 0 above the line and 0 below the line. And we have here 1 and 1 in between the lines. So in this case, we can separate this data set. If you want to use, we solved this problem last time using perceptron, 3 perceptrons, in fact, if you can remember it, because we need to generate 2 lines and we need another perceptron to combine those decision lines. So we can use a perceptron for classifying it. And as you can see here in this MLB classifier, we will have one hidden layer, and this hidden layer will have 2 perceptrons or 2 units, 2 neurons. So it will be like this one. This is the hidden layer, and we will have one output layer. And in this case, also we have 2 inputs. We have x1 and x2. So it will be like this one. So it will be like this one. So we need now to find those parameters, weights, and the pipes, right? So this one, it will be omega 1, 1, omega 1, 2, omega 2, 1, omega 2, 2. Maybe this one, it's V1, V2. We have here B1, B2, B3. So we need to build multi-layer perceptron like this one to classify this problem. So we have this MLB classifier. We can use it for, we can use X and Y for training it. And I'm using also X for just testing it to get Y predictions. You can print out those model coefficients, and you can print out those predictions. If you want to calculate the error, it will be a summation of Y not equal Y predict, multiplied by 100, so it will be in percentage. So now the prediction error, it will be this number in percentage. If you want to plot the decision line, in this case, it's a MLB classifier, so it's difficult to, because it's more complex. So I need to use this approach. I need to, for example, use X1. So X1, it will be all numbers. I need to plot the decision. So we have X1 and X2. So I will generate all X1 points, maybe from 0 to 1.1, for example, because this is the range, right? I will get all those points with a range, with a small step size. And I will get, this is X1 and X2, for example, because X1 and X2, it's the same range, in fact. So I will generate this grid. And I will generate also for X2. So now I have this grid. I will use this function, which is called the mesh grid, to create this X1 grid and X2 grid. And I will send those 2 points to the model for making predictions. And I will use contour plot or maybe this contour function for plotting X1 grid, X2 grid, and YG, which is the predictions. And I will plot also my data points using scatter plot, X1 and X2. And if you want to get the confusion matrix, you will get the confusion matrix between Y and Y predict. And you can plot this confusion matrix. We have a function. I mean, you don't need to do this, in fact, because we have a function called confusion matrix display. I mean, the function which we used last time. So in fact, you don't need to just waste time writing that part. So you have this example here, XOR MLB classifier. I don't have here the result from it, but you can go to this link. And if you want to generate XOR live, you can try to generate a data set which is similar to the XOR, because in XOR we have here 0, 0, plus 1, plus 1, as you can remember. So we can just try to expand it. We can try to generate a more complex data similar to XOR. So now it's 0 group, plus 1, and plus 1. This is how you can do it. I just generated 100 points for each block. And for example, this first one, I will try to generate those random values. And I will try to, so I generated those 400 points in random. And I will add to it, I try to shift it. So try to shift, all those numbers are random numbers, but I try to shift 100 points in that location, try to shift 100 points in that location. So it looks like, XOR dataset. So for example, I will add 0.6 and 0.6 in positive to the first block. So when I add 0.6 and 0.6, I will get that part, right? So this is plus 1. And then when I subtract minus 0.6 and minus 0.6, I will get that part, right? And then when I add to X1 0.6 and 0.6 and subtract 0.6, I will get this one here, right? So it's like this one. You just make it like this one. I generate random values which are located in that place, but I need to separate that part. I need to take one part here and just move it to that section here. And I need to take that part, move it to that section here, right? That part, I need to move it here. That part, I need to move it here, right? So when I add 0.6 to that part, I will move it in that place. That place here, I need to move it just up, right? So and subtract 0.6 to just shift it in that place. So I will add to X2 0.6 and I will subtract it from X1 minus 0.6. So it will come here. So in this case, we will generate this data set. And after that, I will use my MLB classifier, which we used last time. But in this case, because this model is more complex, I mean, you can see here, there is some kind of overlap between, it's complex, more complex, not simple. I don't need to generate 2 lines like this one, because if I generated 2 lines, the accuracy also will be very low. It could be 70%, for example, because there are some black points will be underneath the line, and some blue lines with blue points will be between these two lines. So the accuracy will not be very good. So in this case, I need to generate nonlinear decision boundary. So in this case, I will use my hidden layer, which is very large, 20 neurons in the hidden layer. So it will be the same as the last model, except that I have hidden layers which has 20 neurons. So it will be like this one. This is my hidden layer, which has 20, 1, 2, and 20. The output, it will be just 1, because the output will be 0 and 1. It will be 0 or 1, for example, and I have two inputs, x1 and x2. So just have those connections. So I will train this model using x and y. I didn't divide the data into training and testing. We should do this, in fact. We will calculate y predict. You can print the model coefficients. You can calculate number of cases which is misclassified. This is the error. It will be the number of cases where y does not equal to y predict. So that one will be the prediction error. If you want to plot the decision line, similar also as we did last time, we will generate all values for x1. We will use this mesh grid to generate x1 grid and x2 grid. And I will use model.predict. The input will be x1g and x2g. So we will get the predictions. And I will use this contour function for plotting x1 g against x2g against y predict. So as we did last time. And at the end also, you can try to plot your confusion matrix. And when we plot the confusion matrix, you can see that the accuracy is 100%, right? Because the training set, it is the same as the testing set. This is not the correct way for doing it. So please try to use this train test split. But when we do it, you can see that 200 cases are 200 cases zeros classified as zeros, and the 200 cases of 1 classified as 1. So the accuracy of the model in this case, it's 100%. This is not correct. I mean, you just try to split your data set. And as you can see here, this is the decision boundary. And the decision boundary, it's very, very complex, really. You can see we generated very complex decision boundary. I guess it's overfitting. It's clear that it's overfit my data set, right? Because accuracy, it's 100%. So this one, according to the last part, it might be sensitive to any variations in my data set. Because if you have some small noise here, so imagine that I'm looking into this data point. If we added very small noise to this data point, maybe it will move into this blue section and it will be misclassified, which means that the model is overfitting my data set, right? Because it will be very sensitive for variations in my data sets or noise. So it's better to try to build a model which has better performance in terms of bias. Because this model, it looks like it's overfitting. This model, it's overfitting my data set. I cannot discover it because I don't have a test set. So what we are doing here, it's just very quick because I'm using X and Y for training. And at the same time, also I use X for testing. This is not the correct way for doing it. We need to use a function which is called the train test split. And I should have X train and X test, because this model will overfit my data set. We will not discover it before having this validation protocol. If you train this model another time using it, because I didn't use here in this model, I didn't use random seed, right? So each time when we run this model, we will start from different combinations for those weights. And those weights, it's 2 times 20, right? So the number of parameters here in this model, it will be 2 times 20 plus 20. So 2 times 20, it's 40 weights for this model, plus 20 bias. For the first layer, for this hidden layer. For the output layer, it will be 20 times 1 weights for the output layer, plus 1 bias here, plus 1 bias. So the total number of parameters here, it will be 20 plus 40, which is 60, plus 20, it's 80, plus 1, it's 81. So this model has 81 parameters, which is very complex compared to maybe our data set, right? If you retrain this model one more time, you will get each time you will get different decision boundary. So the first time we got this decision boundary, when you run this model again, you will get another one, right? When you train it another time, you will get different ones. So each time you will get different results, and it's clear because we didn't use random seed, right? We didn't use a fixed random seed. So each time those weights will be initialized by using different set of values. So I can repeat this example using higher order features. So for example, here I'm using here x1 and x2. This example here, this is x1 and x2. Higher order features, you can just try to create a super feature which can help you to simplify your problem. So for example, if I can plot my data using x1, and here we have here x1 times x2, you will get very different data set. So all those black points will be moved to top, and those yellow points will be moved to down. And in this case, it will be linearly separable. So in this case, I can just use a perceptron for solving this problem, and this perceptron will generate this blue decision line. So this is a very nice example, in fact, to show you that playing with features, it can really help you to simplify your model a lot. So in this case, instead of using a multi-layer perceptron for this problem, and using, for example, 81 parameters, I can use for this model just a perceptron. So this perceptron will have two inputs. One is x1 and one is x1 times x2, and the output will be y bias, correct? So it will be just 3 parameters. So I can solve the same problem using 3 parameters, right? So this model, it's MLB with 81 parameters, and it will overfit. Definitely it will overfit. But if you can use a simple model, I mean, you will have much better performance because it will be very straightforward. You will have very good accuracy, and at the same time also the model will be very simple. So if you want to implement this model in IoT device, for example, or in Raspberry Pi or something, it will be okay. But this model really will be very complex. This model, it has interpretability, so it's easy to understand this model. It's easy to explain this model to people, but this model will be very complex. So instead of using x1 and x2, because when you use x1 and x2, the problem will be linearly inseparable. But if you can use x1 and x1 times x2, the problem will be linearly separable, and the solution will be really very, very easy. So try to play with the features before solving your problem. We used this example last time, make circles, which is inseparable data sets. And as I told you also last time, we need to get the decision boundary in the middle here. And in this case, it will be really very complex to do this using a perceptron. We need to use MLB at a minimum, for example. But if we can play with the features, so instead of using x1 and x2, maybe we can use x1 against maybe x1 squared plus x2 squared. So it will be much easier, right? Or just instead of using x1 and x2, it could be x1 higher order features. It could be x1 squared and x2 squared. When we use x1 squared against x2 squared, we can solve this problem using a perceptron. So when we do this, so I used x1 squared and x2 squared, for example, and I will fit the model. I used the logistic regression model, and I used this x and y for training the model for predictions, and the plotting the same way, plotting the decision line. So the decision line will be a circle, right? And this circle has a radius, right? If you want to get this radius of the circle, because this is a decision line, we use the perceptron for training this simple problem. So we have here x1 squared, x2 squared, and we have here a y, and this is +1 bias. So omega 1 and omega 2. So this decision line will be omega 1 x1 squared plus omega 2 x2 squared plus p equals 0, right? So you will get x1, omega 1, omega 2, and bias when you train your model. So finally, you will have this equation x1 squared plus x2 squared equal 0.91 squared. This one will be the radius. So this radius here will be 0.91. So it's very easy to explain, right? So when you play with those features, you can simplify your problem, and when you simplify it, you can select a very, very simple model, and you will avoid lots of problems. If you want to use a support vector machine, you can import it from linear model, and it's called SGD classifier. SGD classifier. It could be those linear classifiers. It could be support vector machines. It could be logistic regressions, which is trained using SGD, stochastic gradient descent, and it is used for, could be used for binary classification problems, and it could be used also for regression problems. The idea from using support vector machine is to get this, you try to create this gap between the two classes, because usually when we use a percept, for example, or MLP, the decision line will be just a straight line, but in case of support vector machine, it will be a line with a gap also, or with a distance between those support vectors. We will use the nearest point here and maybe a nearest point here as a support vector, and we will use those support vectors for creating this gap between the two classes. And the advantage of using support vector machine, it will not be sensitive for noise, because imagine that you have these data points, and if this data points has a noise, it will move a little bit around this location, so it will still above this line, so the accuracy will stay the same, right? Also here, if you have a data point here, plus minus noise, maybe it will move a little bit, but it will not cross this line, so the accuracy will stay. It will give you robust accuracy, even when your data points has some kind of accuracy, because of this gap between the two classes. Because the support vector machine, it tries to maximize this gap between those two classes, so it will give you more robust results. But if you will solve the same problem using perceptron, maybe this data, you will get a line which has, I mean, those data points are very close to each other, for example, right? So for any reason, if you got some noise, maybe this data point will get some noise in the future, for example. So in this case, it might move from above to below the line, and it will be misclassified. So in this case, the system or the model will be sensitive to noise. I want to use this support vector machine for MNIST dataset. So we will import this MNIST datasets from sklearn datasets, right? And it's already divided into X-train and Y-train. So the first 60,000 will be used for training, and the last 10,000 will be used for testing. You can plot those data points. I will use this SGD classifier using random state equal 42 for reproducibility, because I need to reproduce my results. And this is the maximum number of iterations. For example, I will train the model using X-train, Y-train, test it using X-test. You can try to calculate those score, accuracy, for example, precision. You have those. You have all those. You can from sklearn.metric. So those all metrics are coming from sklearn.metric. So you can plot the accuracy, precision, recall. So you can get all those numbers. You can get all those numbers, and at the same time also you can plot the confusion matrix, your confusion matrix. So we try to maximize all data points across this diagonal. And this means, for example, if we selected this one, for example, it means we have 2,047 4 classified as 4, but also we have some misclassified or confusion. Maybe we have some zeros. This one means 4 classified as 0. This one 4 classified as 3, for example, as 1. 4 classified as 1, and so on. So the confusion matrix is very important. So at the end, you will get your results like this one. This is the accuracy. This is the precision. This is the recall. But please, don't report single numbers. Try to report a range. So try to report this one as a number, which is the mean, plus minus a standard deviation, for example. Something like this one. So it will be more, it will be more robust when you try to report it as a range. This example, we use the hold out validation. If you want to use cross validation, you can just use a function called the cross validation from sklearn.model selection. So you will define your model. You will use this cross validation score. The input will be the model and the X, Y, and number of faults, K value, which is 5, for example. And this is a scoring, which is accuracy, for example. And in this case, you will get 5 values in this score. When you print it out, you will get those. For K equal 1, you got this accuracy. For K equal 2, you got this accuracy. For K equal 3. So each time we will have different accuracies. And at the end, you need to report the average accuracy, which is this number. It is the same also. If you are using cofold cross validation, you don't need to report a single number, because this one will be the average or the mean. You can at the same time also calculate standard deviation and report this average plus minus standard deviation. It will be more better. Feature selection, because we are selecting features. I mean, in this example, each figure here, in fact, each digit is 24 times 24 pixel values. right? 28 times 28 pixel values. So it's a very large number of input features. So in fact, we can simplify this problem using a feature selection technique. And the importance of feature selection, it can be best recognized when you are dealing with a data set that contains a large number of features. And this type of data set is often referred to as high dimensional data set. It's a high dimensional data set. And with this high dimensionality comes a lot of problems, such as increased training time and cost, because your model will be complex. If you are working with 28 times 28 features, in this case, you need really to have several hidden layers, and the number of neurons in each hidden layer also should be increased. So at the end, the model complexity will be very high, and then when it's high, it requires more time for training and the more computational resources, and the more data. In fact, we need to get more data, and the chances to overfit will be at the same time very high. So in high dimensional feature set, there might be also several features which are redundant. Sometimes some features are redundant and some features are not important. Some feature does not carry any information for us. So in this case, we try to some features are just extensions or combinations of other features, right? So in this case, we try to select the most important features and simplify our model. And those redundant features don't effectively contribute to the model training. So there is a need, in fact, to extract the most important. There is a need to extract the most important and the most relevant features from this data set in order to get the most effective prediction modeling performance. So it's very, very important to select the most important features from this model. So there are some techniques for feature selections. It enables the machine learning algorithm to train faster. It will reduce the complexity of your model and it makes it easier to interpret. And also it will improve the accuracy of your model if the right subset is chosen. And it also will reduce chances to overfit. So there are lots of advantages of using feature selection. Simplify your model, avoid overfitting. Your model will be much simpler, and therefore it will be easy to explain this model to the people, for example. We have very nice function called the select k-best. This function, we can import it from feature selection, sklearn feature selection. You need to test this one, select k-best. And it's based on statistical tests. It calculates correlations between inputs and outputs, and it will give you those correlation values, and it will sort it according to this correlation. So you will have a chance to select the most features, the most number of features which are more correlated with the output. You just need to define k here, select k-best. You need to define k. So for example, if this MNIST data set has 28 times 28, maybe I can say that I need to select the most important k10 features from those. So this function, it will calculate the correlation between the input features and the target, and it will sort them according to the correlation. So you can pick the most highest correlated features with the target. We can use this example here. We use iris dataset, for example. In this iris dataset, we have 4 inputs. I will define this select k-best. I will import it from feature selection. I will call it selector called select k-best. It will use chi-square. This is a statistical tool, and I will select k equal to because I need to define k. So k equal to, which means I need to select the most important 2 features from those 4 input features. So using x and y, I will transform its fit underscore transform x and y. Why we use x here? Because we are selecting input features. In fact, we use x and y because this function will calculate the correlation between x and y, and it will sort them according to the highest from top to bottom, for example, or from high to low. And in this case, you will have a chance to select the highest, two features. You can get this score. This score will be the correlation. In fact, this score will be the correlation. It's selector.scores. It will be the correlation. When we do this, you will get those numbers. So we have 4 features, x1, x2, x3, and x4. And you can see here the correlation of x1 with the target. It will be 10.8. For x2, it will be 3.7. For x3, it will be 116.3. For x4, it will be 67.04, for example. So in this case, I need to select the highest. So I need to select you can get the index also. You can get those index of the highest. So 2 and 3, it's the index. It's this one. The index is 0, 1, 2, and 3. So when you use this score, when you use selector.get support, you will get the index of the highest 2, and the index of the highest 2 will be 2 and 3. And as you can see here, because the score here is higher, those are the highest, the highest correlated with the target feature. So we can see that in this example, we can see that X3 and X4 are more relevant to my problem. So in this case, we don't need, in fact, to use X1 and X2, but X3 and X4 will, X3 and X, if we can select, we can select X3 and X4, because X3 and X4 will be more relevant to my problem. So in this case, we can just, we got X in U. So in fact, X in U, it will be, X in U, it will consist of, this is the new feature set. So the new feature set now, it will consist of only X3 and X4. So we are just selecting. It will select X3 and X4, and we have, of course, Y. So in this case, I can just train a very simple model using a perceptron using X3 and X4. So in this case, if I need to build a model, I can just build a model using X3 and X4, and we will get very good results, right? So it will be a very simple model. And at the same time, also, I'm selecting the most relevant features to my model. If you want to select 3, in this case, I will select X1, because X1 has higher correlation, not X2. If you want to select 3 inputs, so in this case, I will select X1. So it will be X1, X3, and X4, for example, if you want to select 3 features. Principal component analysis, we can use principal component analysis for reducing the dimension. It's unsupervised technique, which is used for data reduction or compression, and it is used for simplification. So if I need to use principal component analysis, I need to import it from sklearn.decomposition, this one, and I will use it with MNIST dataset, right? So I will import MNIST dataset, and I will divide each pixel value by 255 to convert it to a number between 0 and 1. So we have X, we have Y. I will use principal component analysis. So PCA equal PCA. We need to define number of principal components. So N underscore components, this is the number of features which you want to, number of principal components. This one will be number of principal components, number of principal components. You need to define it. It's hyperparameter. You need to define this number. So the original image here, it's 28 times the 28 pixel values. So I want to reduce it to 8 times 8. So I need to convert this one into a smaller image, which has a size of 8 times 8. So I need to select the most important 8 times 8, 64 pixels. So now it's 64 pixels. I need to select the most important 64 pixels from this 28 times 28. It's dimensionality reduction. I need to reduce it into 64 pixel values instead of using 28 times 28. So I need to import BCA. I need to define number of components. I will fit it using X. It's unsupervised, so we will use only X. We will not use Y. So the last function, which is select k-best, it's supervised because we need to use Y, because it calculates the correlation between X and Y. But in case of principal component analysis, it's unsupervised, so we will just work with X. We can use a function which calculates cumulative sum of explainable variance ratios, for example, and we will get the reduced features. X reduced equal PCA.fit to transform X. So we will convert X into X reduced. X has the original dimension, which is 28 times 28, but X reduced has dimension of 8 times 8. So now we reduce each image into this image, right? If you want to recover it, in fact, we can, this is the original image. We will convert it into this reduced. I will call it reduced. But also, in fact, you can recover the image from this one if you want to recover, if you want to see the impact. So I can recover the image. I will call it recovered. And this recovered image, it will have the original size. It will be 28 times 28. So I will recover this image using this subset of principal components. And you can compare between recovered and original to see the difference. Is there any difference? Do we still have the same information using the recovered image? If yes, in this case, doing the reduction from 24 times 24 to 8 times 8, it will be very good for, it will still carry information. Of course, we will lose some information, but at the cost of reducing the model complexity. So this is the reduction and reconstruction. So this is the original images, which is very nice, high definition. Imagine just each image here, it's 28 times 28 pixel values, and I will use principal component analysis to get the most important 64 features or principal components, and I will use this 64 features to reconstruct the image one more time. And I did the same here. I did this reconstruction, as you can see. This is the reconstructed image using it's using 144 principal components, which is 12 times 12, right? Not 8 times 8. So of course it's still, I can recognize that this image is still 5, but instead of using 28 times 28 pixel values, I'm just using 64 or 144 pixel values to reconstruct this image. So the model, in fact, will see those numbers. I mean, the model will have this information. Of course, the quality is much less, but as I told you, it's a trade-off between the quality of the image and the model complexity, right? It's a trade-off. If you want to train SGD classifier using 144 principal components, this SGD classifier we used it from before. It's linear classifier, linear model. We will use also confusion matrix, precision score, recall score, and we will divide my data sets into, it's already divided. In fact, when you import it, it will be already divided. I define my model, SGD classifier, random state, because I need to reproduce my results. I will train model using XTrain, Y-train, and I will use X-test for calculating the predictions. And I will use model score to calculate the accuracy between X-test and Y-test. Precision, recall, I will get all those numbers. I will plot my confusion matrix. As I told you, you don't need to do this here because we have a function which can do it for us, right? And I will get those numbers. So you can see here, this is accuracy with a star. It's the original model. Sorry, with a star, it's the reduced model using 144. So this is the accuracy of the reduced model. This is the accuracy of the original model. And they are the same, right? They are still the same. Although we reduced the number of features from 28 times 28 to 144. Precision, it's reduced a little bit because the original model, it was 0.908. It has been reduced to this number. And also for the recall, it has been reduced to this number. And it's logic that you will get less accuracy, less precision, less recall at the price of having a simpler model, right? And then when your model is simpler, we know that it will generalize better. So although the accuracy is less, but the performance on long term will be much better. Okay, so now we finished for today. Sorry for taking more time today, and the next time it's in my notes that we will talk about ROC. I need to prepare something for next time, and we will continue next Friday. Yes, do you have any questions, please, for this part? So try to use principal component analysis. Try to use select k-best. It will be something nice in your, maybe if you are writing a paper, for example, you can just try to use select k-best. Try to select the most important features, and also try to use principal component analysis for dimensionality reduction. Yes, I guess, do we have any questions? Oh, okay. I lost many people because now we are 13. So I hope that we have the link also because we have been streaming it to YouTube. So please you can go to the link if you are not attending the last section, for example, but try to look into it. And let us meet next week. And at the same time, also, please try to send me names of reference group. Please, as soon as possible, if possible. So thank you very much for today. And